Hello and welcome to it, Mindsetters. This is Len Extra, your favorite show, and it's on a Tuesday. You know that it means physical sciences. My name is AB Abram, and I'm with Tracy, the Tracy. Tracy, how
I
are you?
like that. The Tracy. Oh, I like that.
Because we have so many Tracy's, hey?
Yeah,
So
but
you're
the other
Tracy.
one's also the Tracy. I like,
Yeah.
she's also really good. I'm just saying.
All Tracy's are the Tracy's, but this is the Tracy for the matriculants.
Of course.
Of course,
'Cause
hey?
we're amazing.
How are you, Tracy?
Good and you.
I'm good, hey? You're so energetic today.
Yeah,
What's
it's
up?
called lack of sleep.
Uh,
Don't tell anyone.
Okay, no,
This
I
is
won't.
what happens.
Uh,
This is when I start scaring my own learners. They all look at me and go,
Oh.
you need more coffee. And I'm like, yeah.
All right. Okay. During the break, I'll get you some. What are we doing today?
Today we're doing chemical equilibrium. So now we're starting a nice section. Last week we did rates, and remember we made the elephant toothpaste? Well, this week we're starting chemical equilibrium, and we're actually tackling the hard part first. So we're going to do the calculations, remembering a little bit of stoichiometry from grade 11. But if we do it step by step, we'll be okay.
Okay. When you talk about calculations, it only means one thing. You need a calculator. So we have this awesome giveaway calculator, proudly sponsored by Casio, and I'll be announcing the winner later on. All you need to do is to answer test yourself questions, get most of them correctly, or all of them correctly, and you could be our winner for today's show. Next week, you can hear your name on TV and also see it on Facebook. Talking about Facebook, we're connecting because I've learned today that through physical sciences, they say we bring earth by being connected to the world. So connect with us on facebook.com/LearnExtra. Like us, share the page, and also tell your friends about the page. Help other mindsetters on the page. #walk together. We don't want anyone to be left behind. On Twitter, follow us at LearnExtra. That's all we have for you. The links, notes are on Facebook, and make sure that you also do the challenge question because it's about challenging yourself.
Great. So
Great.
it's my turn now.
Yes, it's your turn.
Okay, good. And I love the whole Facebook Connect thing. I think it's important because that's how you learn, actually.
Exactly.
Even by trying to answer other people's questions, that's how you learn.
That's
That's why
how
it
you
always
learn.
looks like your teachers know so much. Because we teach it.
Exactly. That's how you get earthed, hey? And talking about it, can you just fill this in?
Yes.
I have a deal that I need to make with the mindsetters. For me to send your shout-outs today, because everyone wants to hear their names on
Yes.
TV, you must ask us a question. That's how simple it is. No question, no shout-out.
I like that.
Deal.
Deal. I like that one. Okay, so today we're going to look at chemical equilibrium calculations, guys. Don't stress about the fact that we also do Le Chatelier's. We're going to do that next week, okay? So there is another section to it. We're doing this over 2 weeks, so otherwise it's too much to put into one show, okay? And what we're going to do is we're first going to discuss what is dynamic equilibrium, specifically chemical equilibrium, and then we're going to discuss the equilibrium constant and do some calculations with it, okay? So let's just jump right in there. And there is your challenge question. Give the equation for the reaction that has the following equilibrium constant expression, where Kc is H2O squared over Cl2 squared divided by HCl to the power of 4 times by O2 to the power of 2. Okay, so I want the reaction that goes with this Kc expression. Okay, you can assume that they're all aqueous, that they're all in gas form. I don't worry about the phases, that's not important, but I do want to see if you can write the equation for me, okay? So make sure you've got that H2O squared, Cl2 squared, HCl4, O2 to the power of 2. Okay, so this isn't a multiple choice question, so you can't guess it, so we'll see how you do. Okay, right. Let's jump into what dynamic chemical equilibrium is. Dynamic automatically tells you that it's something that has to be constantly in motion. Okay? You've done static electricity. You first looked at that in grade 8 and 9. You did a little bit of that in grade 10. You definitely did some of it last year with electrostatics. And static electricity is when charge is not moving. So static means not moving, stationary. Dynamic means that there's something happening all the time. The thing about dynamic chemical equilibrium is that sometimes, in fact all the time, will appear as if nothing is happening. And we'll get to that. Now, in a closed system, so that's the first important thing about equilibrium, is it has to happen in a closed system. And all we mean by a closed system is a system where none of the reactants and products can escape. Mainly, that becomes really important when we're producing gases. If there's no gases as part of your equilibrium system, then it doesn't have to necessarily be a closed beaker with a lid on it, okay, or a jar with a lid on. But as soon as the gas is involved, you have to be able to close the system so the gases can't escape. If the gases can escape, then we cannot create equilibrium. Okay, it's very important. So in a closed system, a dynamic chemical equilibrium is established when, now we did this last week, we looked at rates. The rate of the forward reaction is equal to the rate of the reverse reaction. What that means is it's one of those situations, it's like running on a treadmill, where as fast as you go forward, you go backwards, okay? And on a treadmill, if you run faster than the treadmill's running underneath you, you're going to run off the front, which is not going to be great. And if you go too slowly for the treadmill, then it's going to shoot you off the back, okay? So when you've reached that, is exactly what dynamic equilibrium is. So you're on a treadmill, okay? I don't like to do it too much in public, so it's not fun to watch. But you're on a treadmill, and it looks like you're going nowhere because you're running and running and running, but something's happening. So you're running forward, and the treadmill's band is going backwards, okay? They must be equal. Otherwise, you don't have equilibrium. So the rate of the forward reaction, in other words, as fast as I'm using up all the reactants and creating products, those products are naturally going back to the reactants. These are all reversible reactions, okay? It has to be reversible, and it has to be naturally reversible. In other words, it's got to be something that will naturally go back to what we started with without me having to change conditions, add catalysts, or whatever the case may be. So, for example, if I go zinc plus oxygen, make zinc oxide is not going to, on its own, decompose back to zinc and oxygen. It's very happy being zinc oxide. So it takes far too much energy for that to happen, so it can't be a reversible reaction. When equilibrium is established, the concentration of all the substances remains constant, and no macroscopic or visible change is happening. By macroscopic, that means if I'm now watching the reaction, it will look as if it stopped. No more gas is produced, there won't be bubbles, there won't be, or whatever the case may be, but it'll look as if nothing's happening anymore. But if I could look at it through very special microscopic glasses that could actually see the atoms and molecules, then we'll see that they're constantly moving, okay? But when we go and measure the concentration of all the substances over a period of time, when it's reached equilibrium, that concentration remains constant. So there's no change in concentration, all right? So we get this situation where it appears as if nothing's happening, but it is. It's just that it's all now equaled itself out, okay? So in terms of a graph, now this is a rate graph, okay? It's probably a little light, but that's okay. When the reaction starts, this is reaction rate on my y-axis, reaction course, time on the x-axis, and here the rate of the forward reaction starts very high and then it slows down, and then it evens out. So it starts to go at an even course. This is the rate graph, okay? Forward reaction, very fast, okay? Forward reaction over here, it starts high, okay? Because the forward reaction is fast at the beginning because we have lots of reactants. We pour all the stuff in and say, off you go, okay? Play nicely. While the forward reaction is happening, that creates products. The products then start, as soon as we've got enough of them, to reverse and go backwards. That's the reverse reaction we're now making the reactants. That starts slowly, okay, so almost at zero, slowly, until eventually it catches up and the two rates end up going constant, okay? So this one over here is the reverse reaction, okay? The rates are equal. Concentration does not need to be equal. This is very important, guys. The rates are equal, but it doesn't mean that the concentration has to be equal. So I don't get to equilibrium, and that's what we're going to look at with the equilibrium constant. When I get to equilibrium, it doesn't mean that the amount of reactant is not equal to the amount of product. It depends on the equilibrium, okay? It all depends on where the equilibrium sits. So different reactants end up getting this equilibrium where sometimes they reach equilibrium, but there's actually very little product. Or sometimes they reach equilibrium and there's very little reactants. We actually need to know what that relationship is, because without knowing that relationship, industry has a real problem in creating certain products that we need, okay? So it's very important. So that brings us to the equilibrium constant. Now, Kc, equilibrium constant, is a ratio. It shows us the ratio between the concentration of the products and the ratio of the concentration of the reactants. As a ratio, it has no unit, ever, okay? No unit, first of all. And so it has no unit, okay? It shows the ratio, but the next statement here, temperature is very important. When we do Le Chatelier next week, you'll see that we can shift or we can change the equilibrium position. So we can change by changing different conditions, we can change the amount of product and reactant, but it'll always change to get to the same ratio, except for when we change temperature. Temperature is the only thing that changes the equilibrium constant, which is why in any question they are going to tell you equilibrium was established at 400 degrees, 1,000 degrees, 20 degrees Celsius, whatever the case may be, because the Kc value is temperature dependent. Okay, it is temperature dependent. The Kc value has got meaning. It's not just a random constant because we feel like making you do some calculations in your chemistry exam, okay? If your Kc value is bigger than 1, okay, and by bigger than 1, I mean it can be 1, 1. That's bigger than 1, okay? It means that we have more, the concentration of the products, these square brackets, they're probably new to you, unless you've done this part already, they mean concentration. It is an acceptable abbreviation. You're going to use it often in this section. The concentration of the products is greater than the concentration of the reactants. If the Kc value is less than 1, it means that we've got a smaller concentration of products to reactants. And I'm pretty sure someone's going, hang on, wait, Tracy, what about if the Kc value is equal to 1? I am going to say I'm sure it's possible. I have never seen a calculation where your Kc value has ended up as 1. But if you get a Kc value equal to 1, that just simply means that the concentration of the products is equal to the concentration of your reactants. I personally, and I've been teaching, I'm not going to tell you how long, so then I'm going to feel old. I have never seen a Kc calculation end up with a value of 1. I'm not saying it's impossible though, okay? I just have never seen it. Where do we get it? Now, here I need you to listen to me, please, because there's a little bit of a memory trick that a lot of teachers teach to help you remember how to work this out. You've got to be careful because it's not an accepted equation, okay? So please be careful with this one. These are just general. These are to help you know where we get the values from, but every Kc expression is unique to the equation we get it from, okay? So the basic expression, if we have a general equation, I don't really care what A, B, and C, and D is. It's just the products and reactants. A is my constant. Little a is a constant, like 1 or 2 or 3 or whatever the case. So is B, little b, etc. Like in maths when you have your constant before your variables, okay? My Kc expression is always set up. So when I look at Kc, and this is what some of you teachers might have taught you, is you take the concentration of your products and you divide it by the concentration of your reactants. Okay? That's just a way for you to remember that products go on top of reactants. Please, that is not an accepted equation. Okay? You cannot write that down as the equation and then do substitution. You will not get the marks. The equation comes from taking my products and putting them at the top, concentration of C to the power of C. Whatever the constant is in front of your compound, that's your exponent. So if that's a 1, obviously you can leave it out. If it's a 2 or a 3 or a 4, you can't leave it out, which means you need to learn how to use how to find things on your calculator using x to the 4 or 5 or whatever you might get. D to the power of D. Then over here, this is my reactants. Oh, I like the brown. And that goes to the bottom, okay? So reactant A to the power of little a, reactant B to the power of little b. That's my general reactant. Just quickly before we go to a break. We never include solids or liquids in our KC expression. They are considered to have a concentration of 1. Okay? It only really becomes important if we have a product that is a solid or a liquid, because then it becomes 1 over. But we give them a concentration of 1, so they really don't affect our KC value. We're really just concerned about the aqueous solutions and the gases, because they can have a concentration. Okay? Now I think it's time for a break, and then we're going to jump right into some questions.
Awesome. Here's a quick quote from Sulani Faith. She says, learn as if you were to die. Sorry. Live as if you were to die tomorrow. That was just a joke. Come on.
Learn as if you were going to die tomorrow.
All right, kidding. Vice
Okay.
versa. Live as if you were to die tomorrow, and learn with mindset as if you were to live forever. Mindsetters, it takes that. Thank you so much. And she also continues to say, mindset is the best. Hala Abraham and Tracy, I'm enjoying the show. Thank you so much, Mindsetter. Guys, we'll see you after the break. Welcome back, awesome mindsetters. Remember, guys, I told you to ask your questions, but they should be related to physical sciences. Unlike the question that I got from Ivan asking Tracy, are you human or a machine?
Well, I did say to Abram, technically, I guess we're a biological machine, but it all depends on your point of view. My learners are convinced I come from another planet, so,
You're a human machine.
Yeah,
Simple.
There we go. And I have superhuman hearing. It's all part of my superpowers. And I see things no one else sees. They hate it because I catch them on their phones. It's just, and I hear everything. It's great.
You just, that's what they call a teacher.
Yeah, we superhumans.
You're
man.
superhumans,
Of
eh?
course we are.
All right.
We don't get paid enough not to be.
All
Anyway,
right. Can I just announce the winner?
Yes,
and then you
you
can
may. Go
continue?
for it.
Because I'm sure people are anxious to hear.
yes, go for it.
Right, our winner for this awesome Casio calculator is Mama Tuba Ndivo. Congratulations to you, Mama Tuba Ndivo. This is coming your way because it's about to be exam time. Talking about exams, Tawasiminya also asked on Facebook that, can you guys share some exam tips with us? But the best tip that I could give you, it is to focus, concentrate, plan your work, have a study timetable. It keeps you like on track. The reason why some of us do not know what to study and when to study is because we've got all our minds messed up on everything at the same time. So a timetable helps you to structure your things and your time.
Oh, no, that's a great one. Absolutely. And make notes. You cannot study, I don't care what anyone tells you, just by reading. Okay? Because that's when you fall asleep. And don't study in front of the TV.
But
Except when you're in front of me. This is studying. Okay, watch us.
Okay.
Just saying, I've got to don't study in front of the TV while watching your favorite soap, okay, or movie. Though we're a bit of a soap opera, but that's besides the point. Anyway, let's focus, shall we? Okay. Now, what I've got, and this is nice because this probably most of you have never seen this question before. Yay! So it's not from an exam; it's only just come out. It's the exemplar paper for 2014. So this has come straight from the department, and I have adapted it because they had some other stuff in that we're not doing this week, so I've adapted it a little bit. But this is what you can expect at the end of the year, okay? So this is the sort of thing you can do. And also in terms of study tips, the more past papers and exam type questions you can do, the better. That's how you get better at this, is by practice, 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 okay? And you'll see with all 3 questions we do today, they're all the same. They're all the same concept. So what they tell you is a sample of N2O4 gas is sealed in a container, so we have a closed system, and is heated. Fine. The N2O4 gas decomposes to NO2 gas, and the reaction reaches equilibrium according to the balanced equation. So what we have is N2O4 gas. Remember, there's our nice equilibrium sign, means forwards and backwards, 2NO2, and delta H is greater than 0. Telling us delta H is greater than 0 tells me that the forward reaction is endothermic. That will be important when it comes to looking at conditions and how we can change equilibrium, but we're not going to do that today. The graph below shows how the concentrations of the 2 gases change as a result of changes made to the reaction conditions. Now, this looks different to a rate graph, so it's not exactly the same as the graph we did before the break. But what this is saying to me, okay, first of all, N2O4 are my reactants. So I always start with a lot of reactants. Always, always, always. NO2 is my product, and I always start with 0. In this first part of the graph, the reactants are being used up really quickly, products are being made really quickly, till eventually we get to the stage where the graph is now parallel to the time axis. Over here, because it's now parallel, if I was watching this reaction, it would look as if no more N2O4 has been made and no more NO2 has been made. It will look as if the reaction has stopped, the concentrations are remaining constant. That means equilibrium is established. Then at T3, something happens, okay? We change a condition, temperature, concentration, pressure, whatever the case may be, and then a new equilibrium has to be established, and then we did that again at T4, okay? And then a new equilibrium has to be established. This, we're not worried about how we change the equilibrium for now. I just want you to see how the graph works. Then they say to you, define the term chemical equilibrium. Well, chemical equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. So that's what chemical equilibrium is. The rate of the forward reaction is equal to the rate of the reverse reaction. Nice and easy. Now they say to you, how does the rate of the forward reaction compare to that of the reverse reaction? So now they're asking you about rate at each of the following times, right? Only higher than, lower than, or equal to. And it's the forward reaction to compare to the reverse reaction. So what I'm asking is the forward reaction higher than the reverse reaction, lower, or equal to the rate? So the first one is at T3. Now, if we look at T3, at this point, I know we make a change, but I told you, because it's the part that I've circled, that up to T3, the graph was now parallel, the concentrations are remaining constant, which means that their rates are equal to. Okay, so the rates are equal to over here at T3. Actually, someone's screaming, I'm sure, right now, going, Tracy, you lie, you lie, you lie. And they would be correct. I do lie. I don't lie, I'm just not telling you the truth.
You're just parallel to the truth.
Yeah. Anyway, moving on. Let's correct what I just said to you, shall we? Okay, guys, leading up to T3, they're equal to. So actually at T2, it's equal to. At T3, I now change something about the reaction. And can you see what happens? Let me just take this out so you can see. At T3, over here, can you see that there's a spike in this forward reaction? Well, there's a spike in making N2O4 and a decrease in the NO2. What that tells me is that I've done something to cause the NO2 to be used up and to make more N2O4. If I'm using up the NO2, then that means the reverse reaction is being favored, because when I use up the NO2, I'm making N2O4. Okay? So actually, I've got this the wrong way around. I do apologize. It's higher than, it's greater than, it's faster. Okay? At T2, they're equal to. Because T2, if you look really closely at the graph, T2s actually starts after they become parallel. Okay? After they go parallel to the graph. Between T1 and T2, it actually starts to reach parallel. So at T2, they are equal to each other. But then we get to the fun question. And right now, my learners are all cringing because they know that means I like it, and that means it's probably a little more difficult than you're used to. Okay? They don't believe me when I tell them anything's fun
Just
anymore.
a little bit.
They don't.
A little bit difficult.
No, but then this is what makes it fun. Anyway, so they tell me that initially, so we're going to look at some important, initially, 0.2 moles of N2O4 gas is sealed in a 2 decimeter cubed container, so that's important, and heated to 100 degrees, so that might be important as well. At equilibrium, it's found that 0.19 moles of the NO2 gas has decomposed to form NO2. So in other words, the N2O4 has decreased its number of moles by 0.19 moles, okay? Calculate the Kc constant for this expression. Now, some of you are going, not a chance, Tracy. Far too little information. Not at all. We are now going to do what is known as a Rice table. Some of you might learn this as an ICE table, okay? I add in an extra line, and a lot of teachers do, but it's not necessary for the marks. It's just to help you. First thing we need to know is that the rows on this table are the same regardless of the reaction, okay? So that's where we're going to start. So we're going to start with our table, and we're going to go fine. I'm going to need a heading row over here. I'll tell you how many columns in a second, okay? Well, the number of columns is actually easy. We need one column to write in everything of what we're going to calculate, and then the number of next columns depends on the number of things in your reaction that are gases and solutions. So we only have two N2O4 and NO2. So I know that all I need is 2 more columns other than my original. And then I'm going to add in a line which my learners have last year they named the fearless line. They decided something had to be named after me because it's just something, it's not in any of the textbooks. It's just something I do to remind us where the products and reactants start, okay? Because sometimes we forget. So I put in a double line over here. That's just something I do. You don't have to, all right? A lot of you teachers won't. It's just when you put a double line in there, then you know where your reactants and products end, and it's important for a little bit later on. So we have N2O4, so we're going to put that over there, and we have NO2. And all I'm doing right now is I'm setting up what I need to answer the question. In my first line, I have to have the molar ratio, which is where the R comes from. And this is the, sorry, I didn't want to write that in. The ratio part is from the numbers in front of your balanced equation, okay? So the balanced equation was N2O4 goes to 2NO2, okay? I'm still not going to go all the way up again, so it looked like that. So N2O4 is 1, NO2 is 2. Okay, it comes important later. Your next line is always your initial number of moles. Some of your teachers may have taught you to use concentration. That's fine. It's just sometimes concentration gets a little difficult conceptually when I start adding and minusing things, okay? I'll put some information in there in a second. My next line is called the change line, which will also be in number of moles. Okay, can you see where the word rice is coming from? R-I-C, which then hopefully some of you go, well, that means the last letter has to be an E, and it is, and it's equilibrium. So now here I want to know what my equilibrium, and in this case it's equilibrium number of moles. Okay, but Kc calculations can only be done if you have an equilibrium concentration. So that means I have to add in one more row, okay, over here, and this last row is my equilibrium concentration. Okay? Because it's concentration, this is going to be in moles per decimeter cubed. All right. These lines, so it's Rice table, okay? Doesn't matter. Those lines are the same, regardless of what happens with the rest of your table. Your next step is to go to the information given and write in everything you've been told. So first of all, we started with 0.2 moles, 0.92 moles of N2O4. Brilliant. They told you at equilibrium, it was found that 0.19 moles of the gas is decomposed. So the change in N2O4 was 0.19, okay? And that's all they told you. Happens at 100 degrees. And for equilibrium, I need to know that the volume is 2 decimeters cubed. And I'm sure some of you are going, yeah, right, Josie. Like, I can get to equilibrium from here. Of course you can. Watch. First and foremost, we always start with 0 product. Always, always, always. So that's the first thing I know. Second of all, and this is why I do the double line, we always minus from reactants and add to products. So I had 0.92. They told me I used 0.19, which means 0.92 minus 1.9 gives me 0.919 gives me 0.73. Okay? We all followed me so far, which actually means I can work out the concentration of this one. And I have actually done some of the calculations just to make it a little bit easier. I'm not going to show them all to you. Remember, concentration is number of moles over volume. So that means I'm going to have to go 0.73 divided by 2, which you can write into this block if it's going to make it easier for you. And that means this is 0.37. First line's easy. I'm sure I'm pretty sure most of you okay with that. But now you're going, hang on, wait. Okay, I get, you can probably also say to me, I get why we end up with what we get for N2O4, but now what do we do with the NO2? Because I really have nothing. This is where things get exciting. Now you have to use the mole ratio. This you need to get. This line and that line must have the same ratio. So it's a 1:2 ratio, which means when I look at these numbers, it must also be 1:2. Okay? And a little trick, it's what I tell my learners, it's what we call timesing by 1 over got. I take what I have, the 0.9, and I times it by the mole ratio of the substance I want, and divide it by the mole ratio of the thing I want, I have. So watch what happens, and I do this in pencil, is you go, I'm going to take the 0.9, and I'm going to multiply by 2. Now use your imagination. Can you see when it crosses the line that looks like a multiplication sign? Just go with it. And then I'm going to divide by 1. That's almost like a division sign. So I'm going to multiply by 2, divide by 1, which means this becomes 0.38. Okay, it's a 2:1 ratio. You can go check that. I always make reactants, double line. I started with nothing. I'm going to add 0.38, so this was a bit of a trick question. That gives me 0.38. This equilibrium line does not have to be the same ratio as my top one. It's ratio and change. Those must be in the same ratio. Okay, always, always, always. Then I'm going to take the 0.38 because I need the volume. I'm going to divide by 2. So that gives me 0.19. We've actually done the hard work. Now some of you are going, oh, don't worry, we'll do another one. Okay. From here, now I need to write my Kc expression. Now my Kc expression is the concentration of the products divided by the concentration of the reactants. My products was the NO2, but there's a 2 in front of the NO2 in the equation, so it's squared, divided by the concentration of the N2O4. I found out that the NO2 has a concentration of 0.19. The concentration of the N2O4 was 0.37. And that's 0.19 squared, don't forget the square. We put that into our calculators and we get, now I've put it into scientific notation just because it's quite a small number, it makes it more accurate. If we do it on our calculators, so we can see over here, let's just put this over here. So we go 0.19 squared divided by 0.37 equals, take it out of that. It's actually 0.09756. Now the reason why I'm putting it into scientific notation, it gives me a more accurate answer, because if I had to round that off, and remember it's always to 2 decimal places, round it off, this would actually give me 0.1. See, I'm used to using the things on my, trying to do like I do on my whiteboard. It would actually end up as 0.1. Can you see? That's not as accurate at all, because we'd have to round off from the 7. So rather do it into scientific notation when it looks like that. It it's one of those things that's not that important, but they really want 2 decimal places. Okay, to 2 decimal places and as accurate as possible. And I think we need a break, and then we'll do another one after the break.
So true. Talking about, excuse me, my sisters. Talking about breaks, I think it is when we do not run away from our problems where we take a break. So even when you're studying, you also need to take a break. Don't be too hard on yourself. You need a break, because a break, it is not a way of running away from your problems or your challenges, because when you run away from them, that only increases the distance from your solution. So don't run away. Take a break. Chill. We'll see you after this break. Welcome back, Matrix. Now, looking on the page, facebook.com/LearnExtra, some of you are giving us some questions, and really appreciate that, and also answering the challenge question, which is so good. Keep on doing that. Remember, also, we're going to be giving you a Test Yourself link in order for you to stand a chance of winning this awesome Casio calculator. Here's a quick comment from Tapelo, who says, this page is really helpful, and so is your channel. I'm pretty sure that most of your fans agree with me on this one. Keep up the good work, mindset, LearnExtra. Thank you so much, Tapelo, for that. It is a very cool and sweet comment, and we are going to keep on doing our good work.
Thank you. And you know what, it's nice to know we're making a difference. That's why we're here.
Yeah.
Okay, it's not, in fact, my learners often ask me, do you get paid to do this? Well, of course I get paid, but that's not the point. You know what I'm saying? I actually do it because I know we're making a difference.
Exactly.
And it's so important. And
Even
I'll
if
help
it's
you
just
do
one
that.
learner, you know, making a difference on one person's
That's
life.
all we want. And you know
Exactly.
what, guys? Just so you know, and I'm very privileged. I teach at a very good school. I'm very, very privileged. I make my learners watch the channel. So I make my learners who have me as their teacher. So aren't they lucky? Besides the
They
point.
are.
I make them watch the
Super
channel. In
like.
fact, for all the subjects, not just for science. I go, you don't need to pay for extra lessons. You
Exactly.
can,
But more than that, Tracy, I should just say this.
Yeah.
Earlier on, we got a comment on Facebook from Elena who said, we never had a teacher even from the first term. We never wrote our first term physical science
Wow.
test. So I feel like I shouldn't be watching the lessons that you guys are doing now. But I should say this to all the mindsetters, even if you don't have a teacher, that is not an excuse. Help is out there, and you can still push yourself. There are people who do everything all on their own without any teacher. We've got videos for you guys. We've got all the previous terms work. If you go on our website, we have videos, we have notes. So help is out there. It's up to you. Take that step, because if you're just sitting and say you won't do anything, nothing is ever going to be done. And a quick advice is that if you get to do our work now, when your teacher gets to the work that we're doing now, it'll be a revision for you. So you'll be knowing everything at the same time.
Oh, absolutely. I have, just quickly, we must get this. But I had a learner last year in grade 11 who was struggling, couldn't afford extra lessons because some of those teachers are ridiculously expensive. She went on the website, did all the internet stuff, improved her mark by 15-20%.
Wow.
All by herself.
Wow.
I'm so proud of her. It's one of those things where, you know, that makes my heart glad. 'Cause it's
Ah.
like, you can if you really want to.
You can.
You can
Exactly.
actually put your mind to it, and you can do anything you can. Anything. Okay, so let's quickly answer the challenge question, and then maybe you can see how many people got it right. But I got a feeling you did, because as soon as I got to the KC expression, I'm pretty sure somebody went, oh, okay, I can do it. All right, so remember, the KC expression says to us that it's the concentration of the products over the reactants, which means this part of the equation, that part is actually my reactant part. So I know I'm going to have H2O as part of my products. Okay, and they both have a 2 in front of them. So we've got to put a 2 in front of them in the graph, in the equation. Then I have to have my equilibrium sign. Don't forget that. That's very important. These become my reactants. And this is HCl with a 4 in front of it and a 2O2. Now, if you'd balance this equation like this in a test or an exam, I'd probably mark it wrong, because it really should only be 2HCl, because you always balance it to the lowest denominator. But that's fine. According to what I gave you, you needed to have the squares and the 4. Okay, so that really wasn't that difficult, and I'm sure most of them got it right. So
Most of them.
telling it wasn't really a challenge question. Now I'm going to think of something
99%.
harder for next week. Well done. Okay, so that brings us to, I think we'll have quickly time to do one more. There are 3 questions. Go look on the page. The answers will eventually be on the site so that you can get the answers. Okay, and then we will find some time to answer your questions. Okay, nitric oxide, NO gas, forms in the internal combustion of engines by direct combination of nitrogen and oxygen according to the following reaction. So they give it to you. During a research experiment carried out by initially, this is important, so I've got important words, 1 mole of O2 and 1 mole of NO2 in a 2 decimeter cubed container. I hate it when they do that, but they like it. 300 Kelvin, that would be important once we start changing conditions. It's found that the concentration of the NO, so that's the last part, is now 0.1 moles per decimeter cubed. Calculate the equilibrium constant. Now, I'm going to need three columns plus the one in the front, so that's 4. Before we even start, remember we said that our table always looks the same. So here we go. We're going to have that part, and then we have, let's not have extra little hooks on it. There we go. And we had 2 reactants, which made us 1 product, if I'm correct. There we go. So it was N2, O2, gives me NO. Okay. And then in our lines, we have our ratio. Okay, I'll fill everything in a second. I spend a couple of minutes doing this. Then we have our initial, and this is always, we want this in moles. Okay. We have our change, which is also in moles. Then we have our equilibrium, which is in moles. Okay, and then we have to have our equilibrium concentration. Okay, so, and this part is in moles per decimeter cubed. Now we go, all right, let's write down, first of all, we go back to the equation and we can write down the ratio, which is 1, 1, and 2. Okay, 1, 1, and 2. I'm writing in all the information I know. Initially, we had 1 mole of oxygen, 1 mole of nitrogen. So that's 1 and 1. And at the end, the concentration of the NO is 0.1. Okay, now we've got to do everything else that comes. First of all, the first thing we remember is we always start with 0 product. 0 product, okay? We now actually need to work out this last part of the equilibrium, but first I need to know, so I'm going to work on the one I know the most information on, which is here. Remember, concentration is number of moles divided by volume. Here, I know the concentration, so what we're going to do is we need to do a little bit of a manipulation. Concentration is number of moles over volume. I know that that's 0.1. I want the number of moles. The volume was 2. So the number of moles is 0.2. Okay? I'm timesing by 2 because of the volume. To go from 0 to 0.2, I'm going to have added 0.2. So now I need to know how much I need to minus from the rest. And remember, this is now our ratio. And I said to you, we're going to take this number. Okay, let's do it with this one. And we're going to go here and we're going to go times by 1, divide by 2. I want the N2, I've got the NO. So I'm going to times by 1, divide by 2, and 0.2 divided by 1, divided by 2 is 0.1. I do the same here. Times by 1, divide by 2, 0.1. This one's nice because it's quite easy to see if you got the ratio right. 1, 1, 2, 0.1, 0.1, 0.2. Of course we got the ratio right, okay? Then we go, well, I use up the reactant, so that means it's 1 minus 0.1, 0.9. Guys, please use your calculators. I know for some of you go, no, but why? Because you can do it in your head. I know you can. For a lot of you, I'm pretty sure you can, but sometimes in a test or an exam we make silly mistakes because we're stressed. Okay, so use your calculators. 1 minus 0.1, 0.9. But I want concentration, which means for the concentration here, I'm going to have to go 0.9 divided by 2, 0.45, and that's exactly the same thing. So it's also 0.45. We're done with the hard part. Now we've got to dump it into the KC. I'm rushing a little bit because I know there's lots of questions.
Yeah.
Yeah. Okay. So, KC value, products over reactants. My products with the NO. Okay. Watch. Product is NO, but there's a 2 on the back in front of it. So it's NO squared divided by N2 times O2. So in other words, I've got 0,1 divided by 0,45 times 0,45. Okay, now let me show you on the calculators. Let's put it this side so I can have the equation up, and that's squared. I keep doing that. Okay, so that's squared. So I'm going to go 0,1 squared divided by, I'm going to put in brackets, 0.45 times 0.45 equals, remember we can't leave it as a fraction, and once again it's one of these horrible ones where it's 0,40493 blah blah blah. You're going to put it down as 0,05. Let's rather put it into scientific notation. Okay, and no, that didn't work for me. 7, 3 equals. It not like me. Oh wait, maybe I should actually take it off. Maths display. Alright, so some of you right now are having a good giggle. It's important to laugh from time to time. Okay, so that gives us 4,94 times 10 to the minus 2. It is a ratio, there is no unit. Okay, there is a third question in the notes. Make sure you go and try it. Okay, hit me. Let's see if we can help them.
The first one was, what is Kc?
Kc stands for the equilibrium constant. It's going to come up again in acids and bases, and basically it shows me the ratio between the concentration of the products to the concentration of the reactants, and at equilibrium also tells me whether by the time it reaches equilibrium if I have a lot of reactant or a lot of product at the end, which is important for industrial applications. Okay? Yeah.
Moving right along. Okay.
Or not,
Which one?
because he's
No.
struggling here to read his Facebook page.
I'm starting on top. Okay.
That's what he says. Don't believe him.
Tracy,
Yes.
I want to ask. Okay, I want to ask you. It's in another language. I want to ask you a question. Will I be wrong if I swap the reactant with the product? I mean, if I start with the reactant and divide them with the product, and also starting with second one on the reactant instead of the way they follow each other. That is from Bongan.
You would be. There's no exception to this one. It has to be products over reactants. It's a convention that's been done, and also because we're looking at equilibrium, and it really, in the chemistry we do, it seems a little bit arbitrary, but in industrial chemistry, so when, for example, and we'll talk about the contact process at some stage this year, the equilibrium constant, which is now telling me how much product I end up with, is very, very important, because I need to know whether I get a lot of product. So from an industrial point of view, absolutely it's important, and it has to be product over reactants. You cannot go the other way around, because it's something completely different then.
Okay.
Yeah.
Prince says, can pressure affect the equilibrium where the number of moles of gas are the same on both sides of the equation?
Okay. It doesn't affect the equilibrium constant, Prince. Okay. So when you work out your Kc value, if you change pressure, pressure will definitely change what we call how the equilibrium lies, and we're going to do that in detail next week. Okay, so it does shift the equilibrium or change it, but it doesn't change the Kc value. The only thing that can change the Kc value is temperature. Okay, so be careful, because they try and trick you out with those. In fact, they'll say to you, what is the effect on the Kc value when this happens? And because you're in the Chatelier mode, okay, which we're going to do next week, and you start making all sorts of predictions, which possibly are correct, but you just haven't answered the question, because only thing that changes it is temperature.
Okay, moving right along. Gochi Gwabe says, hi Mindsters, let's say you're given the concentrations instead of initial mole. How do we fill the Kc table?
Okay, if they give you initial concentrations, okay, the only thing that changes then is that you don't need this last line. You can actually do the whole thing in concentration if they give it to you like that. So if instead of moles they give you concentration, all the other steps I did, the ratios, all of that stays the same, though working with moles is a little more accurate, but you can do it with concentration. Often they'll mix them though, so be careful. Often they'll give you one thing as a mole and something else as a concentration like they did with this one. So be very, very careful. It is preferable to do it in moles, but sometimes you can do it in concentration. All the steps stay the same, you just don't need the last line.
Okay.
Yeah.
Olibokeng says, Tracy, why did you have the same value on the table for products on equilibrium and change mode?
I'm not sure where he means that. You know what? There's no set thing that says that. Oh, I think you mean here, maybe. That why are they the same on both sides? Well, first of all, these have the same ratio of 1 and 1, and we started with the same amount initially. Okay? If I had started with a different number of O2, then my final equilibrium would be different, but the ratio here must be the same as the ratio line. Okay? So this line, the ratio line, and the change line must be in the same ratio. Okay, the numbers must work out if you divide by your lowest to get the same ratio every single time. Okay, whether you end up with the same amount of reactant like you did in this case, that all depends on what you started with. Sometimes you do, sometimes you don't. Don't take it as a set that that's what you're going to get, because there's no pattern to this. They're not going to go, well, every time you will, because they won't. There's no pattern to that one.
Okay. Tracy, on the KC expression, do we only exclude solids and liquids? That's from Muzi.
Yes. Only solids and liquids because they do not have a concentration. Or we consider them to have a concentration of 1, and 1 in a division means nothing unless it's at the top. Okay. So it's only gases and aqueous solutions that we need to worry about. And I think we might have run out of time, hey?
Okay, let's just take
Is it-
one more.
Quick one, yes.
What is the difference between forward reaction and reverse reaction?
Forward reaction is when the reactants react to make the product, so it's going the way we want it forward, okay? The reverse reaction is when the products are now reacting to make the reactant, so it's going backwards. It's going back to what we started. Forward is making something new, reverse is making what we started with, basically. Okay,
Okay.
wow.
We've run out of time.
We have run out of time. I will see you guys next week.
Thank you so much, guys. Remember, Mindsetters, keep on watching Learn Extra and aim high so that when you fall a bit low. But the greatest danger is not that we always aim too high. It's that we always aim too low, and then it's too far for us to reach. So aim high, Mindsetters, and stick to it. We love you, and it's been a great show. We love you. Peace.